Restaking is the process of reusing already staked tokens on the proof-of-stake network to secure multiple services and networks, and this will enable the token holders to earn extra rewards from his stake. So here's the plot on the total value locked of restaking, and as you can see from the start of 2024 to the end of 2024, restaking is actually among the fastest growing user case in DeFi, with a total value lock of around $30 billion US. While restaking could boost capital efficiency and help the users to earn extra reward, it is actually subject to slashing risks from multiple layers for misbehaviors. And actually slashing is widely applied by many restaking protocols to discipline the restaking operators, whom you can compare as the validators. So when the operators are deciding whether to attack, you will actually compare the attack benefit and the slashing cost, which is also what has been studied in the previous work by Dovsala, Roughgarden, and Chitra and Pai, in which they found that the higher the slashable stake, the lower the risk of attack. But this has raised one concern, because at the moment in the restaking protocols, most of the stakes are actually delegated from the investors to the operators. Then if the slashing is actually on the stake, burning up the state, then the impact on the operators, the financial cost for the operators upon slashing is almost zero. Then does it mean that the operator will always attacking? Short answer is no, because slashing not only will be burning up the stake, it will also impact the operator's reputation. So if the operator is taking reputation into consideration, then upon an attack, he would actually compare the attack benefits against the reputational loss, which gives rise to our first contribution. That is, we have established a model to quantify the disciplinary power of reputation. Since restaking is concerned with using the same set of stake among multiple networks, then if the restake returns are linear, the operator's profit will actually be the number of networks secured multiplied by the reward per network. And given that, the operators will try to restake across as many networks as possible. This over-dilution of stake would actually hamper the network security. So in many restaking protocols, they have taken preventionary mechanisms to prevent this excessive restaking. For example, in Symbiotic, they have implemented what they call the decreasing rewards for this purpose. And plotted here is the restaking ratio over the restaking score. So the target ratio for the Symbiotic is 3, meaning that the operator, if it is using the same set of stake to secure more than 3 networks, or the same set of more than 3 times, the restaking score will be decreasing, so that the reward will also be decreasing. So from the network's perspective, actually restaking, instead of improving their reward, is actually introducing more risks. So if taking reputation into consideration, the network should avoid pairing up with low reputation operators, which gives rise to our second contribution. That is, in our model, the reputation actually sustains the equilibrium with finite and growing number of networks. So for the sake of time, I won't introduce the empirical findings, but we actually extracted data from Eigen Explorer, which is basically the data from EigenLayer. Our empirical finding is in line with our model setup. Maybe just one figure here, that is the number of AVS secured over time is increasing gradually instead of securing all of the networks at the very beginning. So however, for our model setup, there are in total 4 parts. We'll start with a behavioral operator model in which we assume that the operator is either honest, who will never attack, or malicious, who will always attack. And building upon that, we'll introduce the strategic operator, who will compare the reputational value and the attack gain. With these two, we'll introduce restaking. That is, we're starting from the network's perspective. We introduce an endogenous reputation threshold for restaking, and we'll conclude by introducing tool extensions. First is that we're combining both native stake, in this context is the operator's own stake, with the delegated stake, and compare full slashing versus partial slashing. So in our behavioral operator model, we've made the following simplified assumptions. First, we assume there's only one operator in one network, and there are a population of small risk neutral investors, we assume that all of stakes is dedicated to the operator, and whenever there's an attack, there will be full slashing. So the operator could be honest or malicious with a certain probability, and it will be able to observe the arrival rate of an attack opportunity, which is lambda upper bar. So by Bayesian rule, the market will form this posterior belief on whether the operator is malicious, denoted by mu t, and t is the length of time that the operator is not attacking the network. For the investors are demanding first R, which is the risk-free rate, and another risk premium is determined by the market posterior, and also the external arrival rate of an attack. By paying off the investors the transfer, the operator is earning pi of mu, which is rho, a transfer from the network minus the transfer to the investors. So in this setup, when the market posterior is becoming better, that is, when mu is decreasing, we could observe that the risk premium will be decreasing, so that the profits for the operator will be increasing. And by solving the model, we plot all of the variables against the market posterior, and you can see that starting from a higher mu, when mu starts to decrease, operator's value function is increasing, transfer to investors and attack rate are both decreasing. This is because mu is the rational expectation anticipation, and the average attack rate when mu decreases will also decrease. In the behavioral operators model, the operators are quite naive because the malicious operator will always attack. That is why we introduced the strategic operator, who not only will observe the arrival rate of an attack opportunity, but also will see the attack reward, kappa, which is drawn from a distribution. So upon deciding whether to attack or not, the operator would actually compare the reward of an attack with its own value. And in this scenario, the attack rate would actually be endogenized because it will be decided both by the external arrival rate of an attack and also the operator's value. The operator's value function can then be represented by this following Hamiltonian Jacobian Bellman equation, so in which the second term on the right-hand side is the expected gain from an attack, and the third term on the right-hand side represents the cost for the operator to build up his reputation. By solving the second model and plot it against the behavioral type of model, we can see here that in the second scenario, the operator is having a higher value, transfer less to the investors, and is having a lower attack rate. This is because now the operators will not always attack. Upon receiving an attack opportunity, the operator will actually compare the attack reward with the reputational loss. And this results in a lower risk premium for the operator, so that the transfer is lower, and correspondingly a lower attack rate. So from here, we can see that, that the reputation is genuinely strengthening the network security. Shall we put it just after our topic? Thank you. Up to now, there's only one operator and one network in our system. But for restaking, in our preliminary draft, we'll only allow the operator to secure a second network. And by securing a second network, the attack opportunity will actually be modified by the number of networks here, denoted by n of mu. And we assume that by pairing up with the second network, the other network is actually incurring, paying a matching cost of C. And the participation constraint for the second network will actually be a comparison between its own value, W, against C. With this setup, we can actually solve for an endogenous restaking threshold mu upper bar, in which the second network will be waiting until the market posterior to decrease lower than mu upper bar to pair up with the operator. So in the case of restaking, we solved the operator's value function and plotted here. There are actually 3 in total. So the blue dashed one is the case where there is no restaking. So the operator is always operating one network. The green dashed one is actually counterfactual one, so in which the operator is always operating 2 networks. Well, the red one is the case where, starting from a higher market posterior, the operator is operating one network, and it continues to operate well to build a reputation, and until mu is lower than mu upper bar, it finally starts to operate the second network. So from here, we can see that restaking is giving the operators more value. It's dominating the case when there is no restaking. Same if we plot everything over time, we can see that The green line represents the value with restaking. The blue dashed line is the case where there's no restaking. The operator is earning a higher value. There's a lower attack rate in the system, and there's a jump when the operator starts to operate the second network in the profit and also attack rate. The interesting part here is that even though the operator has not started to operate the second network, the attack rate is still lower. This is because the option value of restaking is deterring the operator from attacking the network. Okay. For the sake of time, I won't introduce the two extensions, but here we introduce native staking. We require the operator to pull amount of Q in order to participate in the network, which results in a decrease in the operator's value, but yet a lower attack rate in the system. Also, we compare full slashing versus partial slashing, in which we found that, okay, with full slashing, the network is more secure, but this will compromise the operator's welfare and also result in a lower restaking threshold because now the market is learning lower. So in conclusion, what we have done can be summarized in this graph. We actually introduced two reputational channels. One is between the restakers and the operators, in which the restakers is posting what we call a belief-based risk premium, and the operators is accumulating its own reputation in order to have a lower risk premium. The second is between the operators and the networks, in which the networks is deciding on an endogenous restaking threshold, where the operator is accumulating his reputation in order to have the opportunity to restake. And from our result, we found that reputation is a significant concern, and reputation is deterring the operators from attacking, even though all of the stakes are delegated to the operator. Reputational concern is also quantitatively significant because we have seen a lower attack rate in the network. And with the option value of reputation, actually of restaking, actually the reputation value is also increasing, and this further disincentivizes attack. And if we require the operator to put its own stake into play, this will further foster reputation accumulation. So our future research after this will first we'll introduce the endogenous native staking. That is, we allow the operator to choose the optimal level of native stake to put into the system. And second, on the operator side, we will introduce competitions among operators and also introduce heterogeneities among networks. With both parties at hand, we'll explore the cascading filters. For the empirical work, so with the data at hand, we'll definitely first test our predictions and also analyze the attacking and slashing events in detail. All right, thank you very much.
Thank you. Hey everyone. So first off, thanks for inviting me to talk a little bit about this paper. And I thought the paper covered a lot of new ground in terms of, I think a lot of the existing restaking models have been very fine-grained relative to this. So just as a sort of my version of a summary, I guess, is this paper really focused on the principal agent problems within restaking, which had not been analyzed historically. I think the majority of the previous papers had really focused on some of the combinatorial problems. The main important thing is that there is a fixed interaction model of this bipartite type where one is attacking and one is honest, which kind of simplified the problem and allowed you to get to this HJB limit that they have in the paper. And then also there's a sort of mean field formulation describing how this works. So I would say the strengths of the paper were really the idea that figuring out how to think about principal agent problems within this world is quite important. I think in general, naively speaking, liquid staking and restaking, despite having, $40 or $50 billion of assets under management, generally speaking, all of the theoretical results are negative in that you should expect people to be attacking all the time. You should expect attacks to be much more successful, etc. So people kind of haven't acknowledged the fact that the principal agent problem actually adds some constraints on the pure sort of combinatorial problem. The other thing that I thought was nice about this paper is that it focused on empirical analysis. I think a lot of the earlier papers kind of were written when there weren't live restaking networks, so maybe that's also a reason there wasn't much historical empirical analysis. But within this space, I think that is actually pretty useful. And finally, I think the mean field model, so when I say mean field model here, I mean the limiting HJB equation that was shown there for talking about how the actions were chosen by a strategic operator. The limiting equation gives you some tractable economic output, so you can actually say something about what happens with replication. I would say the main weaknesses are that a lot of the attacks that have been found in the combinatorial literature, so formulating this combinatorial optimization problem. So I guess the two main papers are a paper by Duracell and Roughgarden, and then a paper by me and Milesh, which is there are some very weird attacks that occur when you're allowed to simultaneously attack many services. So if operators collude to attack multiple services, you can actually have these attacks where they have much less stake than you would think in a normal proof of stake type attack. This sort of means that this model doesn't quite emulate a lot of those attacks, doesn't include the ability for these like multi-service attacks. And so in some sense it's missing that flexibility that the combinatorial models have. And in some ways, the mean field assumptions also ignore a lot of correlations. In order to take the continuous limit, you're sort of throwing away some correlations that in the combinatorial model are forced on you. So I think the main things I would say that could be kind of improved are kind of collecting all the modeling assumptions in one section. I think they're kind of, you know, if you have not read other restaking papers, you might get confused. I think also figuring out a good way to bridge the data analysis with some of the formal analysis would actually be super useful. I suspect there's sort of like a graphical model type of thing you could do to connect the two, and that would you would be able to show that the theoretical results are actually validated in practice. And then I think, yeah, the biggest limitation is the fact that the model really focused on this two-service example. And you know, in reality, if you look at the live restaking graphs, there actually are, you know, hundreds of operators and tens of services. So the combinatorial effects are non-trivial. A natural way to kind of extend the HJB type of limiting equation is to consider some type of structured correlation model. So, you know, hidden clique models, or to represent attacking cartels, for instance. Another thing that I kept thinking about while reading this paper and then comparing it to the combinatorial results is that the limiting HJB equation sort of resembled what you might see in spin glasses. In fact, the n equals 2 component, actually, there is like an exact equivalence. There's a paper of Parisi from 2007, I think, that basically had a very similar looking equation. That sort of suggests that there might be a way of taking the combinatorial papers, so Roughgarden's or ours, and taking a limit that shows there's some equivalence, and then you can kind of connect the two. And that's it.